What's up, guys? It's Alan. It's Alan time all the time. Here we go with another version of graphing, but now we're going to get to some other functions other than our favorite two, which were sine and cosine. We're going to get to the next one of the big three, tangent, and its reciprocal function, cotangent. So tangent and cotangent are a little bit more difficult, which is why we spent more time on sine and cosine, getting the ins and outs of all their different attributes, how to graph their parent graphs, and then do all those translations of stretching both vertically and horizontally, which changes our periods and amplitude, as well as shifting them left and right, which is horizontally, we call phase shift, or up and down vertically. But now, tangent and cotangent. Bring a little bit more to the table because we know tangent of any angle to be y over x. And cotangent, of course, the reciprocal of that, which is why we call them reciprocal functions. And right then and there, you can see we're going to have some issues because there are times when our x will equal 0. And we know that we cannot have that happen. And when it does, we're going to explore that and see what that entails for both tangent and cotangent, as you can see, for both x and y. All right? So when looking at these, we're talking about having issues with all the other trig functions besides our sine and cosine. And again, the reason for that is our denominators will occasionally equal 0. So where do you think our zeros will actually come into play? Hopefully you said at one of our 4 quadrants. We call those quadrantal angles. So depending on what function we're talking about, in this section just tangent and cotangent, we know on the unit circle these values. And so you can see for tangent, we're going to have certain issues, and I'll use different colors to represent each. Tangent is when the x is equal to 0. That will give us a denominator of 0, which is undefined. And so when our x is 0 means we're going to be either on the y-axis straight up or straight down. And for the cotangent, which is just the reciprocal, we will have a y value of 0 when we are along the x-axis, either to the right or the left one. Okay? So since we're going to be talking about a lot of the same types of ideas and dealing with the whole unit circle all the way around, we're going to have more of the same attributes that we just discussed with sine and cosine, and therefore we'll talk about the amplitude, period, and quarters, phase or horizontal shift and vertical shift, and even possibly a reflection right there on that negative. But there will also obviously be some big differences with all 4 of our remaining trig functions, and we're just going to start with the next 2, tangent and cotangent. Okay, so before we start doing any of those changes, we're going to start with those parent graphs. So here's example 1 as a way to kind of explain these. So I still consider this part of the notes, but I'm going to call it also example 1. So as you can see, not too much that's additional compared to what we've already spoken about with sine and cosine, which is why we spent so much time on those. But for tangent, we're still looking at some input value for x. We're calling our angle, and then also some output, which we are given as a y value. So we're going to go back to our t-chart if we don't know how to graph these yet, just to start, and we'll start at 0 degrees or radians. And again, we like radian measurement because when we cut this up into our 1, 2, 3, 4 quarters of 90 degrees, or pi over 2, pi, 3 pi over 2, and 2 pi. Remember, the advantage of using radian measurements is those are all real numbers. This number right here is a little bit more than 3. And of course, that y-axis splits the positives from the negatives, so these would just be the negative of all 4 of those points in our circle. So starting at 0, I'm going to go ahead and draw our circle over here so we can see what these would come out. But then we'll look at the pi over 2, pi, 3 pi over 2, and 2 pi. And we can also go in the opposite or negative direction as well. But let's start with these 5 key points like we did with sine and cosine and see if there's any differences. All right, so now that we have our circle drawn and we are reminded that the tangent of any angle is equal to the y over the x. So our inputs are going to be that x and our outputs are going to be that y. So I know it's a little confusing, but that y and that x, we're talking about each one of these points, these ordered pairs. All right, and we're just going to start by looking at our quadrantal angles rather than any of the reference angles, the 30, the 45, or the 60 in any one of our 4 quadrants. We'll get there. Okay, but to start, we're going to look at that first value of 0 radians or degrees. And remember, we know that it is the y over the x. And since we could label every single one of these, we know, without even looking at the radius of the circle, every one of those values. So the y over the x for this one would be 0 over 1 or 0. At pi over 2 or 90, we'd be up here. That would be 1 over 0, which, do we know how to divide by 0? So if this is our input and that is what we get out, we say that it is undefined for that input, that x, that angle value that we're dealing with here for theta. Okay, going all the way around to pi will put us at 0 over -1, which would again give us the 0. 3 pi over 2 is going to be down here with a -1 over 0, which again would be, if we said undefined again, we do not know how to divide by 0. That's one of the things that we spoke about at the beginning that we were going to highlight. And then back all the way around to our 2 pi, once again, would put us at 0 over 1 or back to 0. So remember we talked about the period of time that it takes for sine and cosine to repeat. Let's see if that same thing happens here, and also talk about what to do graphically when it is undefined, so that we can show you, which is all a graph is, what that means. Right? So obviously we're starting at 0, and so our first point that we're going to plot would be right there at 0. When we plug in 0 for radians or degrees, we get out our 0. Then when we went to pi over 2, we said it's undefined. So what do you think? What could we draw to let them know that when we input 90 degrees or pi over 2, that there was nothing up or down, no output for our y value when we put in that 90 degrees or pi over 2? What do you think? You may have heard this term before. It's called an asymptote. It's spelled weirder than it even sounds. Asymptote is just a borderline. So what we're looking at here is this to represent, you know what this dashed line represents? No values at pi over 2 will come out for our y value, our output. Nothing up or down for that value. And so we know if we were to start and go back pi over 2, whether we're here or there, we know that that y over x would still have that 0 in the denominator. So we're going to have another dashed line there as well. And if you can start to see that pattern, any odd pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2, 7, or even going backwards negatively, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on. So for tangent, every odd pi over 2 will have what is called an asymptote. And it almost sets up these field goal like, for all you football fans out there, this field goal-like feel that, of course, we're going to try to kick that ball right down the middle of it. And so you're going to see at all these pi's, zeros, or negative pi's. We know that we would then have these 0 output values. And so we can just label those. Boom, boom. Any even or odd pi, any pi. We're talking 1 pi, 2 pi, -1, -2, and so on. But what about everything in between? So there's a couple of ways to go about doing this, right? Remember the all students take calculus for this. All 4 quadrants. And this would be quadrant 1, this would be quadrant 2, this would be quadrant 3, and this would be quadrant 4. Same thing here. So we already know what should be positive and negative. And what is an asymptote? Well, remember we said it's a borderline. And so when we're talking about this borderline, that means we're going to approach it, get really, really, really close to it, but never actually touch it, because remember that's where it was undefined. There was no output value for that particular input. So I already know that all students take calculus is what my 4 quadrants represent. And if I was to go backwards, this would be C, T, S, A, or all students take calculus from my 4th quadrant, and then 3rd quadrant, and then 2nd, and then 1st going backwards. 4, 3, 2, 1. So I already know which things are going to be positive and which things are going to be negative. Everything's positive in quadrant 1 between 0 and pi over 2. So that means I'm going to be above this x-axis for all the things that are positive, because everything below it are negative. But how am I going to draw this? Does it just go straight up? Does it kind of curve towards that? How do we know? Well, if you've started to memorize, or if you've already done that back in chapter 2 when we were going over these things, all of those 30, 45, and 60 reference angles that we were talking about, which one was your favorite for tangent? What angle? Hopefully you said 45, which is right in the middle of 0 and 90. We said the tangent of 45 is equal to 1. And that goes for any quadrant. We will have that reference of 1 for a 45-degree angle. And that goes in both directions, positive and negative. All we have to figure out is it going to be a positive one or a negative one? And for the positives, of course, we're going to have the all students take calculus to help us remember what of our big 3, sine, cosine, and tangent, are positive. If we have the reciprocal functions, we just need to know which ones are paired with what. Sine, cosecant, tangent, cotangent, and cosine and secant, of course. All right, so we know that these would be where it's positive, and the other ones would be where they, of course, are therefore negative. So when we're talking about 1s and -1s, well, then we know that this one, because it's 2nd quadrant, sine is positive but not tangent. Here it's positive 1. Here it's -1. And of course, the same thing the other direction. -1, positive 1, -1, positive 1. And that now allows us to look. And I'm going to focus right now at just right and left 90, so that you can kind of see between these 2 asymptotes, what is this thing going to look like? Well, I know everything is positive in this quadrant, so I will start by hitting that 1 and then going up to infinity and beyond. That's why I have the Toy Story background, okay? Just for that joke. And then here, we know quadrant 4 is all negative stuff. So I will hit that 1 and then go to negative infinity. So the look of this graph will be a little something like this. Hits that 0, and that 1 and that negative 1. And we kind of get this, reminds us of a cubic function from algebra. And if you notice, if I go to the very next set of asymptotes, it looks the exact same if I was to draw it in, doesn't it? And same thing with this one. Every single one of these, if I was to continue drawing it, would have that exact same look. So when we talk about the period, the amplitude, things of that nature, you can see why we spent so much time with sine and cosine, because these are definitely different. Okay? So what is the period of time that it takes for this thing to repeat? Can you see that one there? And then this one here? What is that a gap of from here to there? How long for our time period, our angles, would that take to repeat? Well, if this is to the right pi over 2 and this is to the left pi over 2, then that is a distance of pi over 2. That's a distance of pi over 2. So together, that is a distance of pi. With same thing here, if I was to take 3 pi over 2 and subtract this to figure out the difference between it, 3 pi over 2s minus 1 pi over 2 would give me 2 pi over 2s, or pi. That would be the distance between these, again. So you can see that these are a little bit different in that the period of time that it takes is no longer 2 pi, it is pi. That's how long it takes, half as much time to get all the way around. And let me show you why one more time. If you take a look up at my unit circle that I drew, remember this was positive things for tangent, and then this was all the negative things. But then what happens when I keep going? Well, this would all be what? Positive things and then negative things again. So you can see why this half and then this half and then again and again, every pi, it would just keep repeating. So let's explore what would happen also about the amplitude. Because remember, the amplitude for sines and cosines was along that x-axis. If we were at sine, it looks something like this. And that amplitude was that high and that low from that x-axis. And we knew it was up and down a length of 1. Well, what do these arrows mean up here and down here for tangent? What do our values go to? To infinity and negative infinity. So is there technically an amplitude for these? No, but I'm still going to refer to it because it can be stretched vertically, just like we did with that A, that amplitude for sine and cosine. And the only other point that we labeled was the ones and the negative ones. So those are what I'm still going to use as my amplitude, just like we did from the x-axis with sine and cosine. It's still going to be that 1, but now at our pi over 4s, or 45 degrees. So again, although there is not officially an amplitude with these, I'm still going to refer to it as the amplitude, because if I multiplied this by 2 right in the front here, then we know that that would be twice as big in the, since it's not being done to the x, it was being done to the y value. And therefore this would be stretched up to 2, and this one would be stretched to negative 2. And so it would just have a little higher curve for that. Okay? So just giving you the basics here, let's take a look at cotangent now, which remember is just the reciprocal. All right, so here's example 2, which we're just deriving the parent graph of cotangent now. So remember, we're still going to use the unit circle because it's the easiest, a radius of 1. We have all the x's and all the y's for all 1, 2, 3, 4, technically 5 quadrantal angles. And then remember, for any cotangent for any angle, it's always equal to the reciprocal of tangent. So instead of y over x, we're dealing with x over y. So right from the start, we know that we're going to have to be looking at and being very careful to not get a 0 for y in the denominator. All right, so I'm going to go ahead and start by labeling my axes again. So there is, in both directions, my 0, pi over 2, pi, 3 pi over 2, and 2 pi, both the positive and negative. And now I'm just going to evaluate, which again, if you want to use the t-chart, fine. If you'd rather just go over here and use your unit circle, whatever works. And the quicker you memorize this, the less work it's going to be in the long run. So first things first, I'm going to look for the issues. I want to see right off the bat what's going to give me problems. And we said that would be where y is equal to 0. So where is y equal to 0? Right at the beginning. So I know at 0 and pi, we would have our undefined ratio. So at 0 degrees, radians, whatever you want to say, we're going to measure in radians, and hopefully my axes gave it away. Whenever they're using x and y, that means they're usually using real numbers. So we're going to use radians for that. When I'm at 0, I know it's the x value over the y value, which we said is undefined. So right then and there, we're going to draw our dashed line to represent no output value because of this 0 in the denominator. But when we got up to pi over 2 next, now we had the x over the y, which was 0 over 1. And we know if we have nothing divided any number of ways, we get that nothing out. Okay, so as long as our 0 is not at the bottom, we're all good for now. All right, so that would be a 0. Then at pi, which would be here, I'd have my x over the y, which that means is also undefined. So for those values, you can probably guess the pattern here is every 0, 1 pi, 2 pi, because that would put us right back to where our x was 0. And you can do that counterclockwise, which means in the positive direction, all the way around, which is what we've just done to get that. Or you could go in the clockwise direction, negative pi over 2, pi, 3 pi over 2, and 2 pi. And you're going to get the same zeros in the denominator at those same any pi values. And the other ones, really nicely, are going to be 0. So if we go back to our trusty moniker of all students take calculus to help us to see which things are positive and negative, just make sure that you know that this represents cosine, not cotangent. So we're still looking at tangent to find where things are positive and negative. So quadrant 1 is here, 2, 3, and 4. And so we know the positives will be here and here. So that means I will be up here and then approaching that. And then negative here. So down that way. And then same thing here, positive and negative. And should I have maybe found some more things like the 30, the 45, and the 60? No, the cool thing is I can actually just do the pi over 4 or 45-degree angle again, because what did we say tangent of 45 or pi over 4 was? That was 1. And therefore, when we have cotangent was just the reciprocal, then we can flip 1 and still get 1 or negative 1. So again, you can see this thing repeats, and this is what is called a decreasing graph, because as we read from left to right, our y values go downwards. And so a lot of students get these mixed up because they do look so similar. Wait till we start stretching, reflecting, even shifting them around, which we'll do a little bit of as well. Okay, it can be even more challenging. So how can I help you to remember these? Cotangent, you can remember the 0 of cotangent has the vertical asymptote starting at 0, where the tangent did not start at 0 because it doesn't have the 0. Okay? And in order to get a tan, you have to look up to the sun. But in order to hang your coat, it will look a little something like this. Right? So all those little things, nuances can help, but ultimately it's just taking the quadrantal angles with those 45-degree reference angles that are either ones where it's positive or negative ones where it's negative to help you to graph these. All right, so I wanted to kind of do those two examples with you. Again, even more obvious to show you why our period of time that it takes for this to repeat is every pi. Every pi between them. Okay, so that is much different than it has been for the sine and cosine, which was all very simple to remember, one full circle. But for these, both tangent and cotangent, the period is now going to be pi. And the good news is, these are the only ones that have that. All the other ones will be 2 pi. Okay? Which means if we wanted to split these into quarters like we did before, remember it was the pi over 4, which is what I put right there. 1 pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4s, and then 4 pi over 4, which is just pi. Okay, so you can still employ the same techniques as we've done in the past with sine and cosine, but a little bit different with tangent and cotangent because they have those undefined values that yield asymptotes. Don't forget our amplitude. Technically, there isn't any, but we will still call it a 1 for that a value so that we know whether or not it's been stretched at all vertically. All right? So just to give you some more condensed notes of all of this, some of the things I mentioned for our inputs, which we call the domain, that's all written here. And for the range, now that's everything. It doesn't just oscillate from 1 to -1 like it did with sine and cosine. Now it shoots up forever and down forever. Okay. We talked about the period is the big difference in each of these being pi, where it has issues and where it does actually give us x values for our y values of 0 are at the pi or the odd pi over 2s. And then remember, no amplitude technically because there are no max or min values. So that's for your notes just in case you wanted it. Otherwise, you just go and practice and make sure that you got this down. All right, hopefully you're getting the hang of this. Let's try a few more, going a little bit quicker. How can we do this for example 4? Go ahead and pause it, give it a try. See if you can draw the parent graph, and then from there, graph these two little additional pieces, the 2 that's going to affect the x, and the 1/2 that is going to affect the y. All right, hopefully you gave that a shot. I started drawing my axes and tick marks so that I can start filling these things in. But remember, you always want to start with pi for either tangent and cotangent. Now with that, that means I'm also going to be finding my quarters. And then I also know that there's going to be an amplitude change. And that's the easiest thing, so I'll go ahead and start with that. My amplitude is going to change from 1 to 1/2. And again, remember, I want to hit this point home one more time. There is officially no amplitude. But in order to help us draw it, we will still talk about the amplitude as if it still existed. Okay? Then my period. I'm going to take and divide by whatever is being done to that x. Since it's being multiplied by 2, I'll divide by 2. So that is my period. And if I take 1/4 of that, that will give me my quarters, which would be pi over 8. So I can then draw that starting at 0 and going 1 pi over 8, 2 pi over 8, which would be pi over 4, 3 pi over 8, and 4 pi over 8, which would be pi over 2. And again, you can do that in either direction. For tangent, it's definitely good to go in both directions. You always want to make sure you tan on both sides. But for cotangent, it doesn't really matter where you hang your coat, okay, on the positive side or the negative side. And I say that because since it is indeed cotangent that we're dealing with, we know since it has the O, we're going to start at 0 for our asymptotes. And because we know the period is going to be pi over 2, I know I have to get all the way over here. And right in the middle of that is going to be where I kick my field goal between those asymptotes. And then all we got to do is figure out in our first two quadrants what's positive, what's negative, or technically we already know because it's coat. We're going to hang our coat from up here all the way down. But don't forget, there's also the fact that we do have this amplitude, quote unquote, change. So instead of 1, it's going to change to 1/2. So whether you put the tick mark here or you just change your way that you write it, it's up to you. All right? So right in the middle of the 0 and the asymptotes, you will go ahead and put the 1s and negative 1s, or in this case, 1/2 and negative 1/2. And then you connect the dots. And once you have those points, there's one period. If you wanted to do the same thing over here, you could very easily. As I've mentioned, totally up to you on how many periods. If they don't specify, I'm all good with you just doing 1. All right, hopefully you got that. Hopefully it's also getting easier with practice. It will. Just pay attention to details, understand why you're doing what, which is why I make these videos for you all.